You're watching a Channel 98 NBISD TV production.
Pre-recorded live from the basement at the New Braunfels ISD Central Offices. I'm Kevin Corpy, and this is That Geometry Show. Now, in today's episode, I'm going to be introducing you to a fantastically fabulous family of shapes called polygons. We've talked about them a little bit on a previous episode, but today we're going to look at the whole family, okay? Or at least get you started on looking at the whole family. So download those worksheets from the district website and stick around and meet the members. Hope you join me. All right, today's lesson 21. 21 is going to go along with your chapter 10.1 in your Glencoe book. We're going to be talking, of course, about polygons, and at the end I'm going to throw in a little something about area. Okay? Now, we've been working with special types of polygons throughout the year. I've even introduced you to the term already. Some examples were rectangles, squares, and trapezoids. And yes, of course, it seems like the never-ending triangles. They're all over the place. Well, these are all part of the larger family that we do call polygons. And there are many others. You're going to meet some on today's show. But before we start looking at the family, we really need a more precise, rigorous mathematical definition. Mathematicians have been pretty famous or infamous for making rigorous definitions, which some people think kind of overcomplicates it. But it does give us a checklist that we can kind of measure against so that we know whether or not something is a polygon. Today is no exception. So here is the definition of a polygon. A polygon, which is actually derived from the Greek word, literally meaning many angle, is a closed figure, which means that it's going to be connected all the way around, formed by a finite, not infinite, number of coplanar, which means all on the same plane, like anything that can be drawn on this sheet of paper, segments, such that, all right, two requirements. The sides that have a common endpoint are non-collinear. That means they're not on the same line. So here's a line segment, and they're joined right here at the common endpoint, and these are two separate lines, so they are not collinear. If you had them on the same line, they would be on top of each other, and that wouldn't be a polygon. Okay? Number two, each side intersects exactly two other sides, but only intersects at their endpoints. So if I need to have at least two sides, the third side would have to connect the two other sides, and it only intersects at the endpoints. And this is closed because I can shade it in. Now, that, of course, look, there he is again. It's a triangle. He's all over the place. A triangle is a special type of polygon. Well, now that we have the definition, let's kind of get an idea of what are polygons and what are not polygons. These guys right here are types of polygons. Now, notice there's three shapes. And in each of the three shapes, we have a closed figure. Each of these are closed. I can kind of shade without running out of ink in my pen. Okay, they're not open. We have endpoints, line segments, finite line segments. In this case, this one has 1, 2, 3, 4, 5 line segments, and they intersect only at their common endpoints. None of them are collinear. This is our old friend, Mr. Rectangle. And yes, believe it or not, this wacky-looking dude is a polygon. He meets the requirements. He's in the club. He's in the family. Okay? Maybe the black sheep of the family because he's a bit odd looking, but he's still a polygon. And we love him just the same. You got endpoints, you got line segments, and it's closed, so he fits the criteria. So those are all polygons. What are not polygons? Well, here's some examples of things that are not polygons, and we'll try and figure out why they're not. Let's look at this guy here. All right? Kind of looks like our polygon from up here, but notice that he's missing a side. Okay? So this is an open shape. If I tried to shade it, I would be shading outside, and I'll be shading the rest of the planet Earth. Okay, so that is not closed. So not a polygon because it is not closed. All right, let's look at this side. Looks like a pie that someone had a very generous portion of. Okay, that's not a polygon. Why not? Well, remember, polygons are composed of finite line segments, and this part right here is a curve. So these are not line segments. It's an interesting looking shape, but he's not in the family of polygons. Now look at this guy here. Kind of looks like a nice little bow tie. There you go. If you turn it upside down. pretty sharp looking, especially at the points, but it's not a polygon. Why not? Well, notice that we have endpoints here, and look at this line segment. It doesn't just intersect at these two endpoints, it intersects right there in the middle. So it actually crosses another line. So this is not a polygon because it does not intersect at the endpoints, or just at the endpoints. Okay, so now you've seen some that are polygons, some that are not. Now we're going to start classifying them. Polygons can be classified a number of ways. One such way is based on their concavity. C-O-N-C-A-V-I-T-Y, concavity. And concavity is basically another word for the curvature of the shape. Okay? A figure is said to be convex if every line segment that's drawn between any 2 points on the interior of the figure is also entirely inside the figure. If it's not convex, or if you're in the programming you could say else, a polygon is said to be concave. So if it's not convex, if it doesn't fit this requirement, we say that it's concave. All right? Which basically means we can draw a line segment from 2 interior points, and part of it is going to be outside the figure. All right? Let's look at some of those. These figures right here, all 6 of them, are convex. And here's why. I can take this 5-sided dude, and I can draw any 2 points on the interior. Pick one, anyone. We're running out of time. Okay, right here. If I connect those 2 guys, that line segment was entirely inside that shape. I can go to the next one. Pick any 2. Let's keep it along the edge here. 2 points on the inside. Connect them. That line segment is also on the inside. That's going to be true of any of these. Pick any 2 points, no matter how far away or how close they are, on any side or the same side, and when you connect them, they're all inside. That's a convex polygon. All right? Now, are all of these figures polygon? I'm trying to pull a fast one on here. Which of these are not polygons? Well, let's look. This guy here, a little too curvy to be in the polygon family. That's not line segment, so it's a figure, all right. And it is convex, but it is not a polygon. This guy here, you'll meet him again later on in Algebra 2 and in pre-calculus and calculus. He's an ellipse, and he's really nice, has a lot of cool properties, but not a polygon. He belongs to the conic section family, which might be neighbors to the polygons. You never know. So of those figures, they're all convex. Only these guys here, 1, 2, 3, 4 of them were polygons. All right, the following figures down here are not convex. These figures are concave. So notice that the red line, if I pick this point here and this point here, and I connect those 2, I've turned the red line into green, part of this line passes on the outside of the shape. Same thing here. If I pick a point here and a point here, that line connecting them passes on the outside. Now, sure, there are some points that you can pick on the interior that when you connect are entirely inside, but really all we need is one such line segment that will be partially outside to cast him out of the polygon family. All right, here's a couple more examples. We've got one that looks like the Star Trek insignia, and if I connect them, of course, I'm spanning the outside. And here's another guy, an interesting looking figure. Connect them, and again, we're outside. Now again, these are just figures that are concave. Which of these are not polygons? Well, this guy is composed of line segments, so he's good. The Star Trek emblem here looks like it's made of line segments, so he's good. This guy is kind of like our ellipse friend again, trying to sneak in. Too curvy, and this one here is also too curvy. So they are figures, and they are concave, but they're not polygons. Now, every polygon has to have a name, just like every member of the family does, right? You don't just go around saying, hey, you convex 5-sided guy, come here. So these guys have names as well. We name them according to the number of sides, and we combine a Greek-derived numerical prefix, the part in the front, with the suffix gon, okay? For example, pentagon and dodecagon. Some interesting names here. Now, the triangle is a polygon, and the quadrilateral is also a polygon. But these 2 guys are going to be the exceptions because notice triangle does not end in gon, neither does quadrilateral. They do actually have scientific names. but we really don't use them. So you could think of these as being their nicknames, and it's appropriate to use their nicknames. Okay? Now, if we don't use pentagon or dodecagon, sometimes we can actually use the number itself. Like if it has 17 sides and we can't remember the prefix for 17 sides, we can simply call it a 17gon, which is pretty nice. So in that same scenario, we can call it a triangle if we happen to forget the name and we know it has 3 sides. We can call it a 3gon. We can call this a 4gon. We can call a pentagon, you'll see a 5gon. In general, we can refer to any polygon with n number of sides as an n-gon. Now, here's some names, okay? We've got a table here, the number of sides in our polygon, and the names of the polygon. If it has one side, we call it a monogon, and I put some asterisks here. A two-sided polygon, we call a digon. Now, let's see what these asterisks are. If we try to draw a one-sided polygon, it would look like that. That is not closed. It's a line segment. You could think of it as the other 2 line segments being on top, but remember, they can't be collinear. So this is considered an impossible object in Euclidean or planar geometry. Same thing with the digon. If I draw another one that's not coplanar, now it's open. Okay, so it's impossible to connect it without drawing another side. So they are called impossible objects in Euclidean geometry, but I gave them to you because not only are their names fun to say, monogon, digon, but they do have applications in non-Euclidean geometry. Okay, and if you're fortunate enough to go on and study that at some time in your life, you'll see it's a fascinating topic. So for all practical purposes, Euclidean geometry's polygon, the first one is going to be the triangle, scientifically called the trigon. The next is the 4-sided quadrilateral, technically called the tetragon. Now after that, the names are pretty common. 5 sides pentagon, 6 sides hexagon, 7 is a heptagon, 8 is an octagon, like the stop signs, 9 is a nonagon, 10 is a decagon, 11 you might not see too often. It's a hendecagon. And 12 is pretty common. It's a dodecagon. And number 13, my favorite one, a triskaidekagon. Okay, almost sounds like a cracker polygon. But the triska is actually the root for 13. So triskaidekaphobia would be the fear of number 13. And some people actually have that. Okay, and of course, in general, an n-sided shape would be an n-gon. So your teacher might require you to learn the names, okay? So you don't go around saying that particular polygon. You can actually call it by its name. But that's up to the teacher. It's really more important that you identify them and you know how to work with them, which is what we're doing next. When you're referring to a polygon, okay, you don't want to just say that particular hexagon. So we can actually label the vertices with just a consecutive assortment of letters from the alphabet. And what we do is we use the name, so this would be a 1, 2, 3, 4, 5, 6-sided polygon called a hexagon. And as long as we list the letters in consecutive order, we're okay. So we can call this hexagon, and then we can start anywhere we want. So I can start with R, and I'll call it RSTUVW, hexagon that. Or we can call it hexagon, I can start with R and go backwards, RWVUTS. Or I can start with another letter, like V. I can say VUTSRW. The important thing is that these letters are consecutively listed around the hexagon and consecutively listed in the name. Okay, the order is really not important as far as clockwise or counterclockwise. All right, now, notice in this purple convex hexagon that all the sides appear congruent. It's not marked so, but it appears that these side lengths are the same. And it appears that all these angles here are also congruent. Now, those special types of polygons, they have very special characteristics. Of course, purpleness being aside, they don't have to be purple. But if we have a polygon that has all sides equal and all angles are equal, we call it a regular polygon. A regular polygon. And those are the ones primarily that you're going to be working with in class. Now let's look at some regular polygons. Squares, remember from a previous episode, and equilateral triangles are examples of regular polygons. All the sides are equal and all the angles are equal. These types of shapes are not regular polygons. We've got this guy here. He's a 1, 2, 3, 4, 5, 6-sided hexagon. But this side here, looks big, and this side here looks small. And big and small in this case are not the same size, so this would not be regular. This guy here, this rectangle, definitely a convex polygon, quadrilateral, but this is tall or big, and this side here is small. So you can kind of just visually inspect in this case and say that the sides are not equal. This is a cool looking triangle, but this side is small, and looks like the other two sides, both of them, are bigger than each other, but definitely bigger than the small. So yes, they are polygons. Regular polygons, not even. All right? All right, it's time for a little break, but stick around. Don't be rude. Come right back, because I've got a whole bunch of mental food that's going to put you in a very delightful mathematical mood. Understood?
Tim. Hey. How did she get home? Man, I was so high, I didn't... Are we cool? Tim, you know me. That's not me.
We're back. All right, I got a whole big stack of problems that we still need to attack. So give me no flack, and let's give those problems a crack. All right, that's a lot of information, and I know you're probably ready to actually apply this, but before we do, we need one last definition, sorry. We need the definition of the perimeter. Now, the perimeter of a polygon is the sum of all the side lengths. It's as if we were walking around the polygon. How far would we have walked if we walked around the outside? Okay, now, let's look at this example. This example is taken from something that you might see on a standardized math test that you need to pass in order to graduate from high school. Okay, right now we're calling that the tax test, and that's coming up here in April. So let's see how these problems look like. The instructions say the regular polygons below form a pattern. Now the key word is reading regular. Regular in this case does not just mean run-of-the-mill average polygon. No, it's something very specific. It means that each of the sides in these polygons are congruent, and so are their angles. So this would be an equilateral triangle. This would be a square. This would be a regular pentagon, and this would be a regular hexagon. So they're giving us the perimeters, and they're giving us the perimeters in inches. So whenever units are involved, units are very, very important, and they become a nice way at the end of the problem to just give us another check that we've done the work correctly. So perimeters, it looks like they're increasing. Perimeters getting bigger. And notice the side lengths. That's 3 sides, 4 sides, 5, 6 sides. The side lengths are increasing. So it appears that in this diagram, as the side lengths increase, the perimeters also increase. Now the question is asking us, what is the perimeter of the 7th figure in the pattern? Well, we need to recognize what the pattern is. It's saying the 7th figure. So we need to kind of see what the 7th figure would be. This we can call the 1st figure. These are ordinal numbers. This would be the 2nd figure, the 3rd figure, and the 4th figure. So I got to go 5, 6, 7. Looks like I got to go 3 more out there to get to the 7th figure. So how are we going to make sense of all this information? It's a lot of information. Well, in times like this, a chart can come in very handy. Let's go ahead and make a chart. I'm going to go ahead and call the first column the figure number. And the second one I'm going to call the number of sides. Because I know that as the figure numbers go from 1, 2, 3, 4, the sides increase. And I'll do the side length for the next column. And then finally, I'll list the perimeter here. Okay, so let's go ahead and get this in order. 1, 2, 3, 4. And then I've got to keep going after that. That's going to help me see the pattern. And then I'm going to have to extrapolate, basically, and keep going all the way to number 7. So let's go ahead and fill in what we know. The first figure has 3 sides. The next figure has 4, 5, 6. Okay? So we can actually finish this if the pattern continues. This would be 7 sides, 8 sides, 9 sides. So we're going to be looking for the perimeter of the regular, remember, what the name was? It was a nonagon. We're going to be looking for the perimeter of the nonagon. Well, what do we need for the perimeter? The perimeter says it's the sum of the side lengths, and in a regular polygon, the side lengths are all the same. So if we could figure out what the side lengths were for the nonagon, I know that I have 9 of them. 9 times the side length should give us the perimeter. So that's my strategy now. Well, let's see if we can find a pattern on the side length. If I know the first one has a perimeter of 6 and it has 3 side lengths, that means some number plus some number plus some number, all being the same, has to equal 6. Or 1, 2, 3 times some number is 6. So an algebraic expression, 3 times x has to equal 6. That means x has to equal 2. So we know the side length of the triangle is 2. 2, 4, 6. We'll do the same thing. We're essentially going to take the perimeter and divide by the number of side lengths. So if this is 12 all the way around, there's 4 sides, the side length must be 12 divided by 4, which is 3. Continuing on, the perimeter of this one was 20. There's 5 side lengths, so 20 divided by 5 was 4. Now at this point, without even doing the last one, you might be able to pick up on the pattern. The side lengths are also increasing by 1 size. So 2, 3, 4, this one would be a 5. And we can verify here, the perimeter was 30, divided by the number of side lengths is 6, and we get 5. So it appears we have discovered the pattern. Now you can keep on going down. 2, 3, 4, 5. This would be 6, 7, and 8. Now notice there's another way to do this a little more quickly if you picked up on another pattern here. Notice that the side length is always 1 unit smaller than the number of sides. So if we knew we needed a 9-sided polygon, by that pattern we know that its side length would have been 8. That's another pattern that you could have picked up on. Anyway, now we're ready to do the perimeter. I don't need to list all these perimeters to answer the question, and certainly the first 4 were given. But if I have 9 sides, each of length 8, that's 9 times 8, which equals, drum roll please if you happen to have a drum set, 72. Now, what are the units? If I'm walking all the way around, that's going to be inches plus inches plus inches. That should still be inches. So the units are going to be very important. The perimeter of the 7th figure, which is a regular nonagon, would be 72 inches. Wow. A lot of work for one problem. But that's the type of problems you'll see on the standardized test that you need to pass again to graduate. Now it's time for the part of the show we call Say What? Okay, now we haven't looked at area yet, and it was in the title, so it must be time for area, and you'd be right. You're often going to be asked to solve problems involving the area of a regular polygon. Now the area is just the measure of the size of the region enclosed by the figure. Area is kind of like if you think about your parents are getting new carpet. The people laying the carpet need to know what the square footage of the house is. So that's basically the area of the rectangle or whatever the polygon that the shape of the room is. Okay? We're going to be looking specifically at regular polygons where all the sides are the same. Now the area of the polygon, a regular polygon, involves another special length, which means a brand new word that we have to learn, called an apothem. Not to get confused with that cute, cuddly, furry little rodent with the beady eyes. Okay? Now the apothem of a regular polygon is the length of the perpendicular line segment drawn from the center of the polygon. So here's the center. This is the line that's drawn perpendicular to a side length. This right here is the apothem. I'm going to call it A for apothem. It happens to bisect the sides that it intersects, or that it touches over here. So this side length would equal that side length. That's a very important characteristic of an apothem. Now you don't have to draw it from here to here for any particular reason. Notice you can rotate this around, and you can draw it from the center to any convenient side, but it only works for a regular polygon. So that's the apothem. Now for any regular polygon with perimeter P, so we need to know the perimeter, and apothem of length A, the area A is given by the following formula. A, the area, equals 1/2 of P, the perimeter, times little a, which is the apothem. 1/2 PA, half of Paul, okay? It's like the left side of your dad, right? Half of Paul. You can remember that. Find the area of the regular pentagon now with the side length of 20 inches that is inscribed in a circle with a radius of 17. Wow, what does inscribed mean? That means we're starting with the circle, and then inside of that, we're going to put our regular pentagon. So you notice that the vertices of the pentagon touch the outside of the circle. And it's a regular pentagon, so this side length is 20. We know all the side lengths is 20. We also know that the circle, so there's a center, to any point on the outside is going to have a radius of 17. How are we going to use this information to answer the question? Well, we're going to have to start marking it up and drawing triangles. Notice if you draw the radius from the center to a point on the vertex where the regular pentagon happens to touch, this, in fact, creates triangles all the way around. If you drew them all the way around like this, you would create 1, 2, 3, 4, 5 congruent triangles. Well, what's our strategy? Well, you can kind of problem solve if you get the formula. If you can find the area of one of those triangles, you can multiply it by 5. But we're going to go ahead and try to use the formula. We need the area, or the perimeter. If the side length is 20, the perimeter, P, is going to equal the side length, 20 inches, times how many sides we have? 1, 2, 3, 4, 5. So times 5. So that gives us 100 inches is the perimeter. So in the formula, I like to check it off. I have P. Now I need to find the apothem. And this is where a little bit more problem solving comes in. The apothem, I need to draw it. That'll help me see it, won't it? So if I come from the center and I drop that perpendicular to a side length, this is the apothem A. And remember, it bisects the side lengths, which we know to be 20. So I know in this particular regular pentagon, I've created this triangle here. That's a right triangle. And this side length right here, I know to be half of the full side length. So half of 20 is 10 inches. Okay? Now notice that this line segment right here, which is going to end up being the hypotenuse, is just the radius of the circle, so it's 17. And we're trying to find A, which is one of the shorter legs. So guess what we're going to have to use here? The handy-dandy Pythagorean theorem, which might be in a notebook. So here we go. A squared plus 10 squared equals the hypotenuse 17 squared. And now we'll solve. We get A squared plus 100 equals 17 squared, which is 289. Subtracting 100, we get A squared equals 289 minus 100, which is 189. And finally, taking the square root of both sides, we get the exact answer, square root of 189, which is approximately 13.7 inches if you have a calculator. So a little bit of work just to get the apothem. But now that I have the apothem, I have both things that I need in my equation. So I'm going to plug in. The area then of the regular pentagon is the 1/2 times the perimeter, which I found to be 100. I'm going to include the units here because it'll be a good check at the end, times the apothem is the square root of 189. Now I'm using the exact answer because if I use 13.7, I'm going to have a rounding error. And you only want to round at the very, very end. So now if you have a calculator, you can punch this in and you'll get that the area of the regular pentagon with a side length of 20 inches inscribed in the circle with the radius of 17 is approximately 687.386. And if this was in inches, I forgot to include it, inches times inches is inches squared or square inches. So now if you wanted to carpet that little bitty pentagon, you would tell the carpet layers that you need enough to cover that much square inches. Okay? That'll look pretty nice if we carpet it. All right, a lot of concepts, a lot of ideas, a lot of definitions again on today's show. Something that you need to sit down and memorize, and look at it, familiarize yourself before you begin working the problems. You'll be doing yourself a giant disservice if you don't. But polygons, polygons, polygons. Okay, we have to be gone as well. We're out of time, unfortunately. You probably heard enough of me for today, but hey, I'll be back next week. Until then, I'm Kevin Corpy, and I'll see you on the flip side.